everyone who's joined us for the November event from the Engineers Ireland Energy, Environment and Climate Action Division. My name is Bernice Doyle. I'm chairing the division, and I see we've just broken 150 people dialed in. So I think we're good to go at this stage. It's great to see the interest in this event. I'm just going to introduce Chris, but before that, maybe just to note that we will have a Q&A at the end. You should see the Q&A button at the bottom of your screen. So if you have questions as you go through, maybe just put them in there, and we'll start going through those at the end of the talk. So the rapid transition of Irish homes from fossil fuel to heat pumps, it's a really hot topic at the moment, and one of personal interest to me. I'm looking to do it myself, so it's great to get Chris this evening to talk us through this. Chris has a huge amount of experience in the area. He's the environmental engineering director at BDP, a chartered engineer, and he's been involved in a large number of kind of landmark low energy projects in Ireland, to the extent that I think there's over 35 awards for sustainability to his name and to BDP, which is an amazing achievement. So he's got lots of articles and research papers out there, and very importantly for this event, I suppose he's on the committee which drafted the heat pump standard, which was recently published. So really looking forward to hearing from Chris this evening, and I'll hand over to you with that, Chris.
Thank you, Bernice. I'll start sharing the screen now so you can see the presentation. Okay, you should be able to see the screen now. It's good to see so much interest in the topic. I think that means there's a lot of people that all also want to have something to say at the end, so I'm going to try and leave maybe 15 minutes at the end. You can ask questions using the questions feature. But also at the end, it'll be possible to unmute your microphone, well, to raise your hand and have your microphone unmuted if you want to put in a comment or something like that, or make a statement or give a view. So the transition from fossil fuel heating to electric pumps. This is really the second wave of heat pumps. About 15 years ago, there was a huge interest in domestic heat pumps, and it was, I suppose, undeserved really, because the carbon intensity of the national electrical grid was so high that they were worse for the environment than gas boilers. And then it died away, partly died away due to the poor quality of heat pumps that were being installed and the poor quality of the service. A lot of the manufacturers and suppliers were overselling the heat pumps and under-delivering. And but now the second wave is well underway with more advanced equipment and a lot more knowledge about heat pumps. So how is the installations going? Well, for new build, there's been a rapid increase. It's increased in the last 5 years from about 25% of the new build market up to about 65%. And the main reason why it's increased is the changes in Part L. It's relatively easy to achieve Part L if you install a heat pump, and it's one of the easier ways of doing it. There are other ways of doing it. You can use larger amounts of PV and various other technologies to reach the Part L compliance. So it's reached 65%. Probably the full effect of the latest regulations hasn't kicked in, because any building that was designed or got planning before the regulations could still be installed at a lower standard. But that 65% is going to continue to increase, maybe not to 100%, but a long way up. And I've also graphed the increase in electric cars because I don't think you can talk about heat pumps without talking about the electrification of transport as well, because the two technologies are fighting for electricity. So far, about 7% of new cars are electric or plug-in hybrid. The target was to get 10% up by 2020, and I think the target has also shifted slightly, because the original target was pure electric, and now the target has changed to electric plus plug-in. And the intention is to get that up to 100% of market by 2030, so there's a steep curve to climb. I think if it is to get to 100%, then some changes in technology and battery pricing is required, but that is expected. So what about existing buildings? There's a relatively low growth in existing buildings so far, but the Climate Action Plan, which is recently released, aims to change all of that. And the Climate Action Plan has a target by 2030 to get 500,000 existing homes up to a B2 BER. That's about 25% of the current houses in Ireland. And 400,000 existing homes are to install heat pumps, which is a huge number. That's about 20% of existing homes to have heat pumps within the next 10 years. That's about 109 heat pumps a day that needs to be installed. It's a manageable number. Now the 400,000, the 500,000, the 400,000 can be a subset of the 500,000. So part of the upgraded home, part of the upgrade could be a heat pump. And by 2030, the plan is to have 100% of new cars and vans as electric vehicles or plug-in hybrid. By my calculations, if we ramp up to 100% by 2030, then about 18% of all cars. So 100% of cars electric seems like a big figure, but in 10 years' time, you'll still only see 1 in 20 cars on the road being electric or plug-in hybrid. The Climate Action Plan works that out at about 25%, but I think they're assuming a more rapid growth earlier on in the decade, and then is seeming like it's going to be occurring. And then by 2050, all existing buildings have to be net zero carbon. Now that is only for their systems, so only for the heating, ventilation, the lighting, the air conditioning, pumps, those sort of elements. It doesn't include the end user energy, your TVs and cookers and elements like that. And by 2050, all fossil fuel cars will be phased out. And that works out more or less exactly if you consider 100% of new cars being electric by 2030. And then if you think of the cars, how long a car lasts by 2050, all of the fossil fuel ones will naturally be off the road. And to implement this Climate Action Plan, it's a plan, but it's not necessarily legally backed on its own. The Climate Action Bill, which has just been signed, is the method for implementing it. The Climate Action Plan Bill doesn't contain a lot of detail. It's more about the principles, and the key principle is developing a climate neutral economy by 2050. So what about existing homes? Getting that 500,000 up to a B2. Now, if we take into account that over 40% of the housing stock in Ireland was constructed after 1997, it has a reasonable standard of insulation. Well, has some insulation. The 1997 was the first serious building regulation. U values of walls are about 0.4, that sort of level. If you take a 1997 dwelling, it will achieve a C1 if you work out an NG rating, more or less. If you just add a heat pump to it, it brings it up to a B1 or maybe even an A3 in some circumstances. So all we have to do is take those 500,000 houses and add a heat pump, and it achieves that first bit of the target. Now, at the moment, SEAI won't give grant funding for a heat pump for a 1997 house unless you upgrade the insulation, at least to around the 2005 levels. Possibly that's a bad move if we want to get out 400,000 heat pumps into existing houses. It may make more sense to put the money into the heat pumps than the upgrading the dwelling. We'll get on to a bit more about that in the future or later in the presentation. So what alternatives do we have to electric heat pumps? Why are they the chosen method of reducing the carbon of heating? Well, we could use biomass, and biomass started off being reasonably popular once pellets started being produced. But biomass produces significant local emissions. In London, it's one of the main reasons why the levels of particulates and carbon monoxide are so high. And there's also transport emissions associated with getting the fuel to the buildings, and fuel delivery is awkward, having to wait and organize fuel deliveries. So it's not necessarily the ideal, but particularly for buildings in built up areas, in cities. In Dublin, the particulates and NOx emissions are already above WHO limits. Biofuel, bioethanol, elements like that. It creates local emissions and transport emissions, same as biomass. It's also quite expensive, and it's quite difficult to get your hands on it. Some companies like Tesco have done deals to secure a supply, but for the average person or the average client, trying to get hold of biofuel is quite difficult. There's also some ethical concerns about it in the replacing of the planting of food with the planting of fuel. Can reduce the availability of food to the most vulnerable. And then we've heard a lot about hydrogen. Hydrogen is very expensive to produce at the moment. It's also relatively inefficient. If you consider that you have a kilowatt of wind energy available to you, you can put it into a heat pump and you get, say, 3 kilowatts out. If you were to burn it in a boiler instead, well, firstly, you've got to convert it to hydrogen, and you lose about 30% of the energy in the conversion process. And then when you burn it, you lose a little bit more. So it's kind of 60% efficient versus 300% efficient if you use the energy directly. However, the main interest in it is the storage potential. Unlike the wind, we can't store it. And the energy density is very high, which makes it excellent for transport. So it's not going away. Well, what about alternatives using natural gas? Natural gas isn't a zero carbon fuel, but how good can we get with it? Gas engine CHPs, if we were to burn it in an engine, generate electricity, take the heat out, the overall CO2 emissions are actually worse than using a natural gas boiler and electricity from the grid. And of course, it creates local emissions with particulates and NOx emissions. A lot of literature will still refer to CHP as being a low carbon technology. Even if we look at the EGRI's generation capacity statement that was released in August this year, it states that CHP reduces CO2. The maths isn't difficult to do, and if you do the maths, it doesn't reduce CO2 compared to just using a gas boiler and electricity. Then we get on to fuel cell CHP, which has only recently become commercially available in Ireland. And this is really an advanced version of a CHP unit. It's a CHP done properly. The natural gas is converted directly into electricity and heat without any moving parts. It's just chemically converted. This process is about 18, gives out about 18% less carbon dioxide than an electric heat pump when you compare it with the grid carbon intensity of electricity at the moment. So it's better than even better than a heat pump at the moment, but only for the energy produced. The unit available at the moment is quite limited. It provides about 1.3 kilowatts of electricity and 0.85 of heat, and you have to run it continuously. So it continuously gives this output, and if you don't use the output, then the gas is still being consumed. That output doesn't perfectly match a house. The house goes up and down and wanders around. So the question is, what do you do about the remaining carbon if it's only providing a proportion of the total energy for the building? It also requires water to run. It uses about 32 liters of water a day, which is a reasonably large amount of water. And it can't easily reach zero carbon. If natural gas became decarbonized, then potentially it could reach zero carbon. If you were burning hydrogen, you could reach zero carbon, but there's no immediate visible solution for getting this to zero carbon. Then we have natural gas absorption or heat engine, where we use natural gas to drive a heat pump instead of electricity. It's not zero carbon because the gas is still burnt. It can be viewed a bit like a boiler with a 140% efficiency. So it's an incredibly good boiler. The overall emissions from it is similar to an electrical heat pump right now. And the pricing is similar to an electric heat pump. It's a little bit more complicated and more difficult to maintain. Now, this form of heat pump would actually comply with the Climate Action Plan as part of those 400,000. Now, there is still a place for these technologies. particularly where the electrical grid may be poor and you can't get an electrical supply big enough to support a heat pump. They may also start to come back into popularity if the natural gas grid decarbonizes. And decarbonizing the natural gas grid is clearly something gas networks Ireland are interested in because they run the grid and that's their livelihood. And Ireland has a very well-developed natural gas grid, so it would be a shame to let all that infrastructure go to waste. And there is a plan for getting the grid down to zero carbon by 2050. So you could ask the question does it make sense to retrofit expensive electric heat pumps when natural gas is going to decarbonize and we can reach this zero carbon target just by holding on until the natural gas decarbonizes? The difficulty with that is that the plan is to have it decarbonized by 2050, and the plan involves having about 37% of the natural gas provided by biomethane. So that's organic waste being converted into methane, which is effectively net zero carbon. About 13% hydrogen, which is useful for storing renewable energy in particular. The bit I have a difficulty with is the 50% is solved by using carbon capture and storage. So you burn the fuel, you capture the carbon, and then you bury it in the ground. That technology is expensive and is, I suppose, somewhat at the early stages of development. The other difficulty with that is it works very well, or it could potentially work well for electricity generation or very large energy users, but in a domestic house, it's not going to work. We can't capture the carbon at a local boiler. So for domestic users, this solution, you could say it has a low probability of getting us to absolute zero carbon. And how is decarbonizing going with the electrical grid, on the other hand? Back in around 1997, the carbon intensity of the grid was about 800 grams per kilowatt hour. And it has reduced dramatically since then, right down to about 375. And the intention is eventually to go to zero by 2050. And how realistic is that? Well, you can see that a significant proportion of the load is made up by coal and peat, and there is an active plan to phase out coal and peat by 2025, which will leave us dropping down further. Now, part of that will have to be made up by natural gas and part will be made up by renewables, but the figure, you can see how the figure is guaranteed to reduce. If we compare it to natural gas, well, natural gas has stayed more or less steady so far. And then if we look at heat pumps, even an air source heat pump used to produce domestic hot water, so water for washing at 60 degrees, it was better than a natural gas boiler from about 2016 on. And air source heat pumps for heating, well, from about 2008 on. You can see why 15 years ago it didn't make a lot of sense to write heat pumps, because the carbon impact was actually larger than using a gas boiler. But right now, using a heat pump is about twice as good in terms of carbon emissions as a gas boiler. So changing to heat pumps now gives a certainty of improvements straight away. Now, this is based on getting a seasonal coefficient of performance of 3, so 1 kilowatt of electricity out in and 3 kilowatts out. So what sort of efficiencies can we get from a heat pump? If we look at the marketing of heat pumps, we get all sorts of claims. The claims have been more carefully worded in recent years. I've seen many a claim years ago of manufacturers saying you put in 1 kilowatt of electricity and you get 5 or even 6 kilowatts out. More recently, the manufacturers have become more careful about how they word the claims. So here's a couple I pulled off the internet this week. 2/3 of the usable heat comes from a free and sustainable source. Well, that could be true. I think it's a COP of about 3. That seems reasonable. Next one says up to 75%, so that would infer a COP of 4. However, they've used the word up to, which means that it's not particularly claiming anything definitive. The next one says between 2 and 4, but in new systems can be 5. Using the word can be to qualify that. So they're saying, well, somewhere between 2 and 5. It's not really committing to anything in particular. Another one, up to 5 times the electricity. So a COP of 5 is claimed directly, although it says up to. And what they mean by up to is that under certain weather conditions, you get a figure of 5, which isn't really that useful as a metric. You want to know how it performs over the whole year. So if we go to SEAI instead as an independent body and say, well, what do heat pumps do? Their website will say between 3 and 4. So they're giving a fairly safe range. There's very few studies that have monitored the actual performance of heat pumps in domestic seasonally, and there's 2 that are almost always referred to. First is the Energy Saving Trust study, where they took 80 heat pumps and monitored the performance of them. The manufacturers were aware that they were being studied, so they were able to give the best foot forward. This is the distribution of COPs, seasonal COPs. This is a subset. This is after the initial test was done, the manufacturers were given the opportunity to go back and tweak the units, and then they were remeasured again. And you can see none of the units achieved a figure of 3, and they're getting around 2.2. But that was back in 2012, and there's been some improvements since then. UCL did a second study in 2017 with about 700 dwellings, and they're getting a median of about 2.65 for air source and about 2.81 for ground. One of the interesting things there is they're not really getting much of a difference in performance between air and ground, although it's traditionally always stated that ground source gives you much better efficiency. From the monitoring systems, it doesn't seem to be true. So even these figures are much lower than that 3 figure I was using back here. But that's 2017, and products have improved a little bit since then. But I think if you see claims of over 400% efficiency, then you need to start treating them with suspicion. And I suppose the average performance is quite important to us, because we're talking about a large scale plan of 400,000 heat pumps. We don't want to know that one heat pump can possibly get a COP of 5. If it's only run in warm weather, we want to know what is the average for typical usage of heating. And the difference between ground source and air source is closing in terms of its carbon performance. If you imagine the extreme scenario in 2050 where the grid carbon density is 0, it doesn't matter whether you run a ground source, it doesn't matter how efficient or inefficient the heat pump is, it's still producing 0 carbon. And then if you throw that back, you can see that as time goes by, the difference between ground source and air source is reducing. And given that air source is cheaper, there is more of a move away from ground source. The other difficulty with ground source is if it's poorly designed, it can be less efficient. I've seen a lot of ground source systems that have been undersized, and to compensate for that, the temperature is lowered. So where in an air source system, if it was 7 degrees outside, you're working with 7 degrees. With a ground source system, quite often the flow would be at -6, -8 even. And that's with that graph is with an assumption that there's 20% difference in performance, whereas there was 6% in the monitored performance. Is an interesting one. The more efficient we make a building, the less efficient the heat pump becomes. So if you think of a new, very efficient fabric for a building, well built, well insulated, airtight, heat recovery, ventilation building, the efficiency, the amount of energy used is a lot smaller, but the efficiency of the heat pump is worse. And that's because the external temperatures are lower when the heat pump is required. So when it's warmer, you don't need to turn the heat pump on. So if you take a new dwelling, say it's below 10 degrees, you don't need to turn or above 10 degrees, you don't need to turn the heat pump on. That gives you an average temperature of about 6 degrees. In an older dwelling, anything up to 15 degrees, you need to turn your heat pump on. And the average is about 8.5. So there's a difference in temperature. Also, the newer building will spend more of its time in defrost cycles, which accelerates the drop in efficiency. The other factor is that there's a large proportion of the energy is domestic hot water, which has to be generated at 60 degrees, where the heating might be generated at 40 degrees. So that reduces the efficiency of the heat pump. In a well-insulated dwelling, the flow temperature can be reduced, but not for the domestic hot water. So the net effect is that it's a less efficient. And what this is getting towards is that retrofitting heat pumps is more efficient than installing them in new dwellings, because the energy usage is larger, so you're saving more, there's more energy to save, and the heat pump efficiency is better. So if you had a fixed amount of money to spend on heat pumps and you could install them in newer buildings or older buildings, you'd get a better carbon saving by installing them in the older buildings. So that's the question, is it better to invest in fitting heat pumps to a large number of poorly performing dwellings than to share funds between fabric improvements and heat pumps in new dwellings? So if you've got a fixed amount of money, should you start adding insulation to buildings, or should you just look for the worst buildings that you can put a heat pump in and put the heat pump in, and then you make the biggest savings for a fixed amount of money? And this is really questioning the fabric first mantra that is the staple of sustainable design. Now, another part of this question is it carbon and cost optimal to improve insulation in buildings if the gas and electrical grids are approaching zero carbon by 2025? It costs, there's a carbon cost in making insulation, so that's known as embodied energy, the energy it takes to make the insulation materials. And if you take an extreme scenario like 2050, every bit of insulation you add to the building is increasing the carbon that's used, because there's no energy used, but there is energy used in carbon in producing insulation. But if we don't go to 2050, if we go to the current scenario, I've done a graph here with the U value on the bottom, and this is mineral wool insulation, this PIR insulation, so high density insulation, and this is the total lifetime carbon emissions. So it takes into account the embodied energy of the insulation and the heat that escapes through opaque elements. This is particularly to do with opaque elements, walls and roof and floor. So when you improve the insulation value more than 0.2, you actually increase the carbon used. So by adding insulation, you're increasing the overall lifetime carbon emissions of the building. And it's even more dramatic if you're using PIR. That's because the energy used to make PIR is considerably more than the energy used to make mineral wool. And this little chart takes into account the difference in density of the two materials. So this is for an equal U value. So there is also an argument to be made that it may be better to retrofit insulation at a later date. So it may be better to install heat pumps now and come back and install insulation later on. If a better form of insulation is produced that has less embodied energy in it. We need a replacement for PIR anyway, because there is significant fire issues with PIR in facades. So there may be an alternative produced which has a low embodied carbon, but also the carbon used to produce insulation is reducing as the grid intensity, the carbon of the grid intensity reduces. Even looking at the 2019 Part L, that has a U value of 0.18 for walls. That's already less than carbon optimal. So at the moment, building to the building regulations uses more carbon than if we didn't build to the building regulations. And this effect increases as we approach 2050. So as the carbon impact of the heating systems reduce, the effect of the materials that we use increases. Now that argument is also relevant to what you build a building out of, and concrete usage and other materials as well, but purely in terms of insulation. So what approach should we take to retrofitting? Well, if we improve the thermal performance of the worst housing stock and prioritize in particular the pre-1990 stock, that's about 60% of the housing stock, before adding insulation to dwellings that are partly insulated. So rather than offering grant funding for insulation for anybody who wants it, it would be better to offer it to those with the worst performing buildings and concentrate the money on those. That's where the biggest savings are to be made. Minimize grants to homes that are reasonably well insulated. Same point. Concentrate funds on retrofitting heat pumps and dwellings that have a poor insulation level, but not too poor. I'm saying not too poor because if you put a heat pump in a very old building, it will find it difficult to heat the building because the temperatures are lower. But certainly 1997 level buildings are better to fit heat pumps into than 2005 dwellings. And we need to start considering the embodied energy impacts of materials in buildings. Historically, it hasn't been that big an issue because the amount of carbon used by the energy use of the building was such a large factor. Now that that's reduced, the embodied energy becomes more important. Excuse the cough. Another question we wanted to address was, can the electrical grid actually support this growth in electric heat pumps, both the new heat pumps and the older heat pumps, the retrofits? So we need to look at the generation capacity. Can we create enough electricity, and can we distribute it to where it needs to get to? And then is there enough endpoint capacity in the actual homes to use it? So we look at those questions. What's the context of that generation capacity? Well, the targets for retrofitting heat pumps will mean that there'll be about 1.3 gigawatt of electricity required for retrofitting and about 1 gigawatt for new build by 2030. Now, the max demand on the grid to date has been 6.7 gigawatt, and the generation capacity is about 10 gigawatt, but that doesn't mean 10 gigawatt is available. There has to be a certain reserve capacity, and there's always some plant out of use. So if we graph it, if we put in new heat pumps, retrofit heat pumps, and electric vehicles, it's about 30% of the existing capacity. That does ignore non-domestic buildings and the electrification of heat in those. So is there a plan for this? Well, the plan is in the All-Ireland Generation Capacity Statement, which has just been released in August, or updated this year in August 2020. Now, the main concern in that document seems to be data centers. So the increase in demand for data centers is considerable and seems to be taking more of a priority than heat pumps. By 2030, 27% of all demand will be from data centers. I looked at the previous version of this report, and the figure was 31%. So the forecasts for data centers are reducing. I think that's mostly because data centers were overestimating what they need when they apply for electrical supplies. This graph also shows the estimated energy usage, not the peak power usage, but the actual energy usage over time. And the residential one seems to be almost flat up to 2029. So it doesn't look like the heat pumps have been included in this. And the reason for that is because this graph was copied from the previous version of this report. They appear to have forgotten to update the graph. And in the previous version, they'd included for new heat pumps, but hadn't included for retrofitting of heat pumps. And that's why it's more or less flat. I think in the new domestic buildings, they were also assuming that a new domestic building would come with PV, and because we're talking about energy rather than peak power, the PV partly cancels out the extra demand. So why were they thinking that? What can PV do to energy demand? Well, if we cover a full roof in PV, like the one in the image, then we can provide about twice the amount of heat that a heat pump requires. But it doesn't really help in terms of peak loads, because the peak load on the heat pump is first thing in the morning when there's no solar available. And then if we look in that document at the forecasting of maximum demand, this has increased. If I compare this with the one in the previous version of the report, and it jumped up by almost exactly the amount of the 400,000 missing heat pumps. And it does allow for domestic heat pumps, it does allow for electric cars, and it does allow for data centers. So the plan includes providing the generation capacity. And this is about a 30% jump in generation capacity that's required. You can see that the predicted total is still below 9, so it's still below the current generation capacity, although you need about a 30% overhead in generation capacity, which means we need to jump up by another 30%. The demand uncertainty between the different forecasts is really related to likely data center investment over the time. I'll just point out that the axis starts as 6. I particularly dislike graphs that start halfway up the axis, because it gives the impression there's a much larger jump than there actually is. This is only 30% of the total. So what about the predicted fuel mix? The total generation capacity available, you can see, well, it has to stay. For fossil fuels, it's staying more or less the same. This doesn't mean the utilization is the same. It'll be used a lot less, but particularly the gas will be sitting in standby while the renewable energies kick in. So by 2025, you can see the coal disappears and the peat disappears, and we're left really with gas. And by 2030, the aim is to about 70% renewables in the generation. So a lot of this is standby. And then by 2050, presumably what happens is this gas is absorbed in carbon capture and storage, which then brings the electrical supply down to zero carbon. Now, what about endpoint capacity? The endpoint capacity of a dwelling is 12 kVA. So you get a 12 kVA allowance. That's slightly under 12 kilowatts. The electrical engineers won't like me converting kVAs into kilowatts, but you get somewhere between 10 and 12 kilowatts from it, depending on your the type of demand that you have. So a heat pump in a new building would be about 3 kilowatts. In an very old building, it would be about 5 kilowatt electrical input. So that's the same as 1 kettle in the case of a new building and about 2 kettles in the case of an old building. So it's not a huge demand for a heat pump. So if you were to put a heat pump into an existing building, there really wouldn't be any issue with endpoint capacity. The difficulty comes when you, or approaches when you also add an electric car. This is why I said the electrical cars were important at the beginning. If you have a plug-in hybrid, typically they come with a 3 kilowatt connection. So adding 6 kilowatt to the demand, this is a typical demand for a building. If we add 6 kilowatt to the demand, we're going to still be well below the 12, and there's no difficulty having a heat pump plug-in hybrid. If you put in a full electric car, you may decide to put in a rapid or a more rapid charger, the next level up for charging, which would more or less fill a 60 kilowatt hour battery overnight quite comfortably, is on light rate electricity, is 7 kilowatts. Now that actually decreases slightly over the night because the battery can't maintain the full rate of charge. But if we were to add a 7 kilowatt electric car and a 5 kilowatt heat pump, you can see we start getting very close to the maximum allowance. Now I've actually tried it. I've tried turning on a 7 kilowatt electric car and a charger, and turning on the kettle and turning on the cooker and turning on the tumble dryer, and as engineers do, I wasn't able to get the main MCB to trip. So it is actually, there must be a little bit of extra allowance on that 12 kVA built in, as you'd expect there to be. But you can also get a charge controller which will reduce the power that's sent to the car whenever your demand approaches the 12 kVA. And your typical profile, if we add in the car, is you'll charge it during the night from 11 o'clock right through the night, and the load reduces a bit as the battery charges up. Then the heat pump, if you have a large heat pump, it'll kick in quite early in the morning and give you a maximum demand. So this is really the point at which we go over that 12. And if we have a demand controller on the car, it'll simply mean that the load pulls back further on the car. So the result may be that your car isn't completely fully charged. Now, most people will find they only have to charge the car maybe twice a week anyway. So it's not a big a deal. It's only for those who are doing very long journeys. Say you were traveling 100 miles a day and you needed to charge your car every night. You may find that you may get into a little bit of difficulty. Also, if you had multiple vehicles, if you had several cars that you need to charge and you tried charging them both at once, you'd obviously run into problems. It is possible to increase your MIC to 16 kVA relatively easily. You just make an application to DSB. There's a small charge for it. But in most properties, that would be possible. Your typical house won't need to do that by adding a heat pump and a typical electric car. What about the distribution capacity? I've spoken to the ESB networks. about their approach to developing the network for heat pumps and electrification of transport. And the electrification of transport is probably more of a concern than the heat pumps. And the after diversity maximum demand is already adjusted for new housing estates. So this is already taken into account for any new developments to the network. They are allowing for the infrastructure for it. In existing estates, a gradual increase in demand is catered for. There shouldn't be any difficulty in most estates. What would or could cause the difficulty is in particularly some of the older estates, if everything was changed at once. So if there was a scheme where everybody in the estate was to get a heat pump, that would clearly have to be coordinated with the ESB networks to upgrade the local infrastructure to deal with it. A gradual adoption of transport is likely to stop those step changes as heat pumps or cars are adapted over the next 10 years. Now that may mean that a coordinated approach to retrofit may be better than simply providing grants and leaving the market to its own devices. It may be better to find an old estate or like 1997 estate and try and retrofit or make an offer to retrofit heat pumps to a large group of houses together, and then the ESB could be consulted on upgrading the infrastructure at the same time. That would also provide efficiencies in terms of installing. You'd be able to get a much better deal for installing heat pumps as well. So what about mitigation? We could use batteries to get us a bit more headroom on the demand. And a battery can be used twice. We can use it to store PV energy during the day, but then we can store up night rate electricity to counteract that peak demand first thing in the morning. I've run a couple of simulations on PV. Quite often when people are looking at PV, they just work out how much energy is produced and then work out the payback based on assuming they're getting all that energy. But often quite a lot of export happens. The blue line is the typical house demand. And if I put in 10 square meters of PV, you can see the bits in yellow are the bits that are exported. Once I go up to 20 square meters, which is half the roof area, you can see almost half the electricity generated is exported. So let's do the full yearly simulation instead of looking at it today. If we simulate it over a full year, if I increase the size of the collector and then look at the percentage exported, you can see for 2 square meter collector, there's about 10% exported to the grid. Once we get up to about 12 square meters, we're exporting about 50%. And you can see how this affects the financial payback as the collector size increases. Simple payback, assuming no grant from SEI and constant cost rates. It's about 15 years and it just increases up. Now, if we add in electric cars and heat pumps, you'd expect this should increase because we can use more of the energy. So I add in a car and an electric heat pump. The dotted line is the previous graph. So you can see that it's the utilization has improved considerably. So 12 square meters will now drop from that 50% down to about 30% export. If we cover the entire roof in PV, we're still exporting about 50%. And you can see the financial benefit improves with the larger collectors as well once the demand has increased. Now, what about battery storage? Battery storage has that potential to bring down those MICs as an alternative to applying for more capacity. We switched the graph around and graphed by battery size and just with 2 different collector sizes. If you have a 22 square meter collector, as the battery size increases, once we get to about 8 kilowatt hours, we're using almost all of the energy. But with a large collector close to the full size of the roof, we're still exporting about 30% of the energy. Your typical power wall, you get into different sizes, maybe 3 kilowatts and 6 kilowatts. So they're relatively small batteries compared to a car battery, which would be about 30 kilowatt hours at the moment. And the payback period, well, as the battery gets larger, it curves down a bit and appears to make slightly more sense, but it doesn't really give you a payback. There's a very little justification for batteries with PV because using the battery, also using it at night to charge it with night rate electricity as well as the PV degrades the battery. because current battery technology only has a certain number of charge rates before, or charge cycles before the storage capacity drops. However, costs of batteries are falling dramatically, and also the battery degradation is improving considerably. So this payback is about to start becoming beneficial for batteries. So that's in terms of energy, but how does it help the MIC? Well, the max demand tends to occur only at that short period in the early morning when we have the car and the heat pump running together. And the crossover is about 6 kilowatt hours. So a 6 kilowatt hour battery would cover that crossover. And that would avoid the need for demand controller and could take up that difference, but would also mean that you can get a complete charge on your car, even if you're driving a long distance. So I think the battery can improve rapid charge convenience, and that may be the main motivation for getting it, is that you can charge your car a lot more reliably if you have a battery rather than trying to store solar energy or other elements. There are plans in the Climate Action Plan to pay for export to the grid from PV, which will improve the cost of PV, but it reduces the chance that you'll purchase a battery. So what about the costs of PV? One option for an existing building is to use a high temperature or heat pump, high temperature heat pump. If we were to put in, say, a 16 kilowatt air source heat pump capable of delivering 70-degree water, heat pumps are best if they're delivering water about 40, 45 degrees, but it is possible to get them to deliver high temperature water. You can use 2 heat pumps in series as a cascade, or you can use a high temperature heat pump. Even if we're delivering at 70 degrees, we can put on a weather compensator so it's operating more efficiently for a large proportion of the year. The supply cost of this is 7,000 at the moment, ex-VAT, so it's quite expensive. So by the time we've actually installed it, paid for the labor, alterations to the system, it's about 10,000, including VAT. And then we can take out about 2,500 for a replacement boiler, because in an old building, you'd probably be replacing the boiler anyway. Brings the cost down to about 7,500. There's no real payback in that method, so the payback is more than the lifetime of the system, assuming no grant funding towards it. The alternative is to add low temperature heaters, so we can maintain that 40-degree water temperature and get the heat pump working much more efficiently. And you could use something like a convector, a fan boost radiator. So you can replace your existing radiator and wire it up. And there's a series of little fans, almost like little computer cooling fans above a finned convector. And that allows you to use water temperatures around the 40 degrees in an existing building. There's an extra cost for swapping all those out. So I'm working that out at about 5,000 by the time you've done all the wiring for a typical house. And if we have a seasonal coefficient that reaches almost that 3-figure average between heating and hot water, we get a simple payback of 30 years. Or with the current grant, at the moment you get a grant of 3,500, which will bring that down to 21 years. But it's still above the lifetime of the unit, so it's difficult to persuade 400,000 houses to put in heat pumps with the current grant. I think you'd almost need double the grants available to persuade people to do it. The cost of doing that would be about 2 billion for that 400,000 replacements. There's also penalty options. We could look at setting minimum standards for rental properties. There's about 500,000 houses rented in Ireland. If we were to say, well, you can't rent your house unless you've got a B1 rating, and one way of doing that is getting your heat pump, and we'll give you a grant towards your heat pump. It may be a solution to get that done quite quickly. Probably not fair on the people that rent houses, but it is a solution. There's also tax increases on carbon emissions, so you could make it worse for those using gas boilers. And the plan in the strategy is to have 80 euros per ton by 2030. That's about 1.6 cents per kilowatt hour for gas. So gas is what, 5 cents a kilowatt hour at the moment, so it's almost 1.5 out of 5. So it's an increase, but it's not enough to make the difference to force you to buy a heat pump. You could also ban fossil fuel boilers and say, well, you're just not allowed to install them. And there is bans on installing fossil fuel boilers in new buildings in the UK from 2025. Although it happens naturally in new buildings by the regulations, you could introduce a ban for existing boilers and just say you're not allowed to install them. That would require some financing though, because it's difficult enough for people to find €2,500 when their boiler breaks. And if you're asking them to find 7,000, there's a lot of families just wouldn't be able to come up with that kind of money. So there is a financing required, whether it's a payback through your bills or some other form of financing system, and would have to be coincided with a ban. Some potential issues with heat pumps. One issue is that as heat pumps are growing and the fabric is improving, there is a natural tendency for heat pump suppliers to offer heat pumps that also provide cooling, which then increases the amount of energy use. This was an advert I pulled off a website, which just says whether you're renovating your home, you can use an air source heat pump as an ideal solution for heating and cooling. Now, I'm sure if the person whose website I took this off is listening, they'll point out that the brochure was taken for a house in Spain or somewhere like that. But it is still a point that cooling will become an issue. So it's an issue also, we were talking about the importance of not over-insulating buildings. If we over-insulate the buildings, then they can start overheating, and then we start using heat pumps to cool them down, and the unintended effect is extra energy usage. We could prevent that with legislation and just say you're not allowed to use heat pumps for cooling, but that's not happening at the moment. Yeah, other technical issues. If you have several electric cars, that could become problematic. Probably won't be a problem coming up to 2030 because there won't be many people with 2 electric cars. 70% of cars will still be on fossil fuels at that point. Common faults with heat pumps, getting close to the end of the presentation. Owner misunderstandings, misleading advice from suppliers about efficiencies, we've talked about that. Misunderstanding about how underfloor heating works in low demand buildings. So some clients will want high temperature floors because they'll want to walk around in their bare feet and feel the warm floor. But if you have a building which is a very low heat demand, then the temperature of the floor is going to be very low and you're not going to get that effect. And I spent some time trying to explain to somebody that you can't just increase the temperature of the floor without increasing the temperature of the house. Some confusion over control strategies. Some suppliers will say leave the heat pump on 24/7, unlike a boiler. The difficulty with that is it actually uses more energy because the house is hot for longer, so it loses more heat. Lack of understanding how to remove airlocks and underfloor heating systems. If you're used to radiators, quite often I've just found the underfloor heating system isn't working, or it's incorrectly connected. Probably 50% of the time an underfloor heating system is put together, each circuit will be connected to the wrong valve, and sometimes that's never fixed. Installation errors. Undersizing was particularly rampant with ground source systems. I've seen a lot of ground source systems where the client has been sold it as having a very high efficiency because it's ground source, but the capital cost is low because the ground source collector is undersized, which means it's actually less efficient than an air source would be, and it's unable to meet the heat demand. System volume. If you put heat pumps are a bit more complicated than boilers. If you don't have enough water in the system, heat pumps don't like intermittent loads. They don't like kicking in and out. That's mostly solved with modern variable speed heat pumps, so the problems are becoming less and less. Poor location of evaporators. You can see an example here where you just have to think of a few more things you'd have to think of than if you had a boiler. If you boiler, it just works. Here we have to make sure that there isn't a flood or snow or leaves blocking our condenser. Just needs a bit more maintenance. Controls also are often not optimized. There's a 2% improvement for every 1 degree change in flow temperature. So if you put a weather compensator that says it's a warm day today, reduce the temperature of the water, that'll dramatically improve the efficiency of the heat pump. So I don't think the heat pumps are designed or controlled to be as efficient as they could. So to conclude, to give you guys a chance to talk, rapid growth in electric heat pumps is an essential part of the solution to decarbonize heat. And the question isn't, can it happen or when will it happen? It is happening, and it's happening now. Heat pumps are rapidly growing despite the cost, particularly in new building, not so much in existing building, but it's about to kick off in existing buildings. Challenges produced by increasing electrical demand can be met and have been planned for. All of those involved in the electrical grid are planning for it and understand it. So the challenge will be met. There may be some instances where you can't put heat pumps in, or you can't put in a large number of heat pumps in a particular area over a short time period, but it can be dealt with. Multiple electrical cars in one household will be an issue with the infrastructure, but probably not till after 2030. You'll still need alternatives for long journeys, but remember, by 2030, 70% of cars will still be petrol-based. And plug-in hybrids are a great solution as well. You can make your local journeys on electric and your long journeys on fossil fuel. Not after 2050, but it'll drag things out. Deep retrofit is not cost optimal in the context of decarbonizing the grid. So deep retrofit used to be the mantra, but keep in mind that it may not actually produce the best carbon performance. And priority, in my opinion anyway, should be given to improving the worst performing properties, because that's where the largest savings can be made initially. While PV and batteries can smooth demand, there's a limited motivation at current cost rates. Costs are, however, rapidly reducing both for PV and batteries. Battery costs for homes will reduce dramatically as second-hand batteries become available from the electric car market, which will rise exponentially over the next 10 years. I think we also need an independent island-specific seasonal efficient study on domestic heat pumps. Even worldwide, we more or less only got those 2 studies of how heat pumps perform in real life. It would well be worth, if we're intending to put in 400,000 heat pumps, it would be worth knowing exactly how they perform, and also how their performance can be improved through controls, which units perform well, which ones don't. So that brings us open to discussion time.